Could you break it down for me like I'm 5?
Absolutely.
Yeah.
Imagine the neuron cell membrane as a busy border crossing. The sodium-potassium pump is like a diligent border guard, constantly working to keep the right number of sodium ions outside the cell and potassium ions inside.
Hmm.
It's a bit of a two-for-one deal, pumping 3 sodium ions out for every 2 potassium ions it brings in.
Okay, so it's like maintaining order at the border, making sure everyone's in the right place. But why is that so important for the neuron to function properly?
This separation of charges creates an electrical potential difference across the membrane. It's like charging up a battery, creating the potential energy needed for the neuron to fire when it receives a signal.
So the sodium-potassium pump is like a tiny generator constantly working to keep the neuron powered up and ready for action.
That's a great way to think about it. And this powered-up state is what we call the resting potential. But the real excitement begins when a neuron receives a strong enough signal to trigger an impulse.
Right. You talked about depolarization, how sodium ions rush into the cell, causing a rapid change in the electrical charge. It's like a sudden surge of electricity. But how does that trigger a signal that travels all the way down the axon?
Think of it like a line of dominoes. When a stimulus hits that first domino, it tips over, setting off a chain reaction all the way down the line. Similarly, when sodium ions flood into a section of the neuron, it depolarizes that section, triggering the next section to depolarize and so on.
So the signal is like a wave of depolarization traveling down the axon.
You got it. This wave is the action potential, the nerve impulse itself, carrying the message from one end of the neuron to the other.
Okay, so depolarization is like tipping over that first domino, initiating the nerve impulse. But what happens afterward? How does the neuron reset itself?